Okay, true or false? If y is a solution of a system and k is any constant, then k plus y is also a solution.
False.
False. What is also a solution? K times y. That one's false. Okay. A solution that looks like k1 y1 plus k2 y2 is called a blank blank of y1 and y2.
Linear combination.
Linear combination.
Oh gosh.
You didn't know that? Don't buy this expression.
Yeah. Hey, Rob, what's up?
If y1 and y2 are both solutions of the system, then y1 plus y2 is also a solution.
That's true.
Yes. Yes.
Did you write that one?
Alright.
How do everyone do?
I was having a little bit of trouble following through with the.
Okay, so in addition to new concepts today, we're also going to be spending most of today's class writing things in vector form and matrix form as opposed to two equations. Okay, so that's what we learned how to do last class. So I'm going to be making you do a little bit of translating just to sort of develop your fluency so you can go use either notation. So remember, a linear system looks like x prime equals ax plus by, y prime equals cx plus dy, which you can also write as a matrix equation. X prime y prime equals a, b, c, d, that's your coefficient matrix, times x, y. And then you can name your vectors with one bold letter and your matrix with a capital letter. All right, so here's a linear system. Y prime is 2, 3, 0, negative 4 times y. And so if I was going to translate this, before we get into the actual question, I'm just going to translate this into a couple of different ways of writing it. So first, a bold y prime, that's indicating that that's a vector x prime, y prime, equals my matrix A, which is 2, 3, 0, negative 4, times a bold y. That means that that's actually a vector xy. And then I can do matrix multiplication to actually break this up into two separate equations. So this would be equivalent to x prime equals, take your 2 and your 3, your row 2, 3, dot product it with x and y, and you get 2x plus 3y. And then y prime, take the dot product of 0, negative 4, and xy, and you get negative 4y. So those are three different ways of writing the same system of equations. All right, so I just want to verify that these two vector-valued functions, vector value just means that the input is t, but the output has two components. So it's a vector. The output is a vector. I want to verify that these are solutions to the system. So because this is a bold y1, that actually means that x1, y1, right? That actually means it's a vector. Is e to the 2t and 0. So it says that this x1 is e to the 2t, y1 is 0. Okay, and then y2, again, that's a bold y2, so that means that that's x2, y2. That's another vector with another solution, negative e to the negative 4t and 2e to the negative 4t. So I'm being asked to verify that both of these are solutions to the system above. So to show that something is a solution, you have to show that it satisfies both equations. All right, so let's do.
Both solutions.
They are, but we need to verify it. I'm going to do this one in a different color so we have them separated. X1, Y1, that's X2, Y2. Okay. Yeah.
So these are solutions for, like, these are the general solutions for our differential equations for x and y, right?
They're not general solutions, but they're solutions. Yeah.
checking that they are solutions.
Yes, we're just verifying that they're solutions. There might be other solutions, right? The general solution encompasses all solutions in one equation, right? But these are two specific solutions.
Do we need a coefficient matrix to check, see whether or not they're solutions to the?
Yeah, you need to know the original system.
Okay, so we're okay. I'll say that that's.
Yep. Yep, this is my original system, and I'm saying, are these two things solutions to it? Okay, so let's check. So I need to plug into the original equations. So my original equations are x prime equals 2x plus 3y, and y prime is negative 4y. So I'm plugging in, I know x and I know y. X is e to the 2t, y is 0. All right, so what is x prime then? If x is e to the 2t, what is x prime?
2e to the 2t.
2e to the 2t. And I'm checking, does that equal 2 times x plus 3 times y? So 2 times x, which is e to the 2t, plus 3 times y, which is 0. Is that true?
Yes.
Yes. Okay, so that part checks out. So put a check there. All right, and then my y prime equation, y prime equals negative 4y. Okay, so if y is 0, what is y prime? 0. So does 0 equal negative 4 times 0?
Yes.
Yes, okay. So this is a solution. It satisfies both of my differential equations. So this one is a yes. Let's look at the one over here. Okay, so I'm going to start with my x prime equation, 2x plus 3y. And in this case, x is negative e to the negative 4t. So what would x prime be? 4e to the negative 4t. And we're checking, does that equal 2 times x, which is negative e to the negative 4t, plus 3 times y, and y is 2e to the negative 4t, given. Are those actually equal? Yes. Check. All right, then we check the y prime equation. So if y is 2e to the negative 4t, y prime would be negative 8e to the negative 4t. That should equal negative 4 times y, and y is 2e to the negative 4t. Are those equal? Yes. Okay, both differential equations are satisfied from the system, so this is also a solution. So we verified that both of those vector valued functions are solutions. Okay, so next thing I want to check out is y1 of 0 and y2 of 0. Okay, and I want to know whether or not they're linearly independent. So if you were here for linear, you'll remember that. And if not, don't think about it until after we have the vectors. Let's figure out what they are first. So remember, y1 of t is a vector valued function, and it's e to the 2t and 0. That was given, right? I'm just using the given y1 and y2 from up here. So, and then y2 of t, this is negative e to the negative 4t and 2e to the negative 4t. So what I'm being asked to do is to plug 0 in for t. y1 of 0 and y2 of 0. So y1 of 0 just means plug in 0 for your t's, so I'm going to get 1, 0. And y2 of 0 is going to give me negative 1, 2. So I've got two vectors, 1, 0 and negative 1, 2, and the question is, are they linearly independent?
Yes.
Yes. So if you took linear, just as a reminder, two vectors are linearly independent if one is not a multiple of the other, right? If one is not a multiple of the other. So 1, 0 and negative 1, 2, one is not a constant multiple of the other, so they are linearly independent. So these two vectors, we call them linearly independent. Geometrically, you think of linear independence as two vectors that don't lie on the same line through the origin. Okay, so now I want to verify, I know y1 and y2 are both solutions. I already verified that. I want to verify that this linear combination of y1 and y2 is also a solution. According to the reading, it should be, right? So let's just quickly verify it. So y3, first I need to get a formula for y3. Right, it's 2 times y1, and y1 is e to the 2t 0, plus 3 times y2, which is negative e to the negative 4t, and 2e to the negative 4t. And I'm just going to simplify this. When you multiply a vector times a scalar, what do you do? Multiply both entries by the scalar. And then when you add two vectors, you add component-wise, right? Add the first entry, add the second entry. So this is going to simplify to 2e to the 2t minus 3e to the negative 4t and 6e to the negative 4t. So I need to verify that this is the solution. So I have to do both my two equations. So start with x prime is it 2x plus 3y? Yeah, 2x plus 3y. Okay. So what is x in this case? Yeah. Yeah, the first entry in my vector is my x entry. This y3 with an arrow over it, that means that this is x, y, right? x3, y3. So my first entry here, I'll just kind of circle it. And this is x3. Second entry is y3. All right, so if that's x, that first entry on top is x, then x prime is its derivative, so that's just going to be 4e to the 2t plus 12e to the negative 4t, right? Okay. Does that equal whatever you get when you do 2 times x, 2e to the 2t, minus 3e to the negative 4t. Somebody's ahead of me. Good. Plus 3 times y, and y in this case is 6e to the negative 4t. Is that going to turn out to be equal?
Yes.
Yeah. So I have 4e to the 2t when I distribute the 2. And then I get negative 6 plus 18 gives me 12. Yeah. So that one works. And then let's check the y prime equation, which is just negative 4y. Okay, so y prime in this case is negative 24 e to the negative 4t. Does that equal negative 4 times y, which is 6e to the negative 4t? Are those the same?
Yeah.
Yes. Okay. So we verified it's a solution. Now I want to evaluate y3 of 0. That just means plug in 0 for t. So if I plug a 0 into my y3, what I found up here, I'm going to get 2 minus 3 is negative 1, negative 1, 6. Okay so far? Okay. All right, so I've created a direction field for this system using WinPlot. This is x and y for my system. And I have 3 solutions. I gave you 2 and said verify that they were solutions, and then the third one is a linear combination of the first 2. So I want to plot those three solutions on my direction field, y1, y2, and y3. So I need an initial condition in order to follow the vector field, or the direction field. So I need to know y1 of 0, y2 of 0, these are my initial conditions, and y3 of 0. And I've calculated all of these already earlier in my work. So this
those vectors not locations or
yeah, that you can think of them, they are representing an x and a y, which we have decided to plot in an xy plane. Okay, so y1 of 0 was 1, 0, y2 of 0 was negative 1, 2, and y3 of 0 was negative 1, 6. All right, so I'm going to plot each of them. 1, 0 has as its initial condition this point right here. That's y1. And it looks like the vectors are just pointing straight along the x-axis. So I gotta. All right, so we plot 1, 0. We follow the direction field. It's just heading along the x-axis. So this is the solution curve that corresponds to y1.
Quick question.
Yeah.
We're going to assume that these, the vector paths will never cross because of the uniqueness theorem.
Right?
That's what I'm asking.
They never cross, correct?
Okay.
Yeah.
So when the vector's going off in infinity, we can assume that the other vectors will never actually reach.
We'll never cross it. Yep, yep, that's true. Yeah. Okay, and then y2, it's got as its solution, its initial condition, negative 1, 2.
does that approach 0 or does it approach the negative x-axis?
It approaches the origin. Yeah, it just goes straight in towards the origin.
It looks like it would kind of towards it and then hook left all of a sudden.
It's really hard to tell with just a direction field,
Yeah.
but that actually is a straight line pointing right at the origin.
Because for me, I just want to follow that, like, close to the x-axis. It just seems like that's the difference.
Yeah, it's not. It's not. Again, this is a drawback of the direction field and its qualitative nature. Right? It's hard to tell. So, but I'm telling you that that one goes directly to the origin.
Oh, geez. The second. Oh, geez, Rick.
All right, and then y3.
Just when they think you gotta figure that out, so you put it on the stage.
Okay, y3. The initial condition is negative 1, 6. Negative 1, 6 up here. And this one hooks, right? This one like starts to come down, but then ends up asymptotic to the first. And that's not a coincidence. Like y3 was a linear combination of y1 and y2. y1 and y2 were straight line solutions, and the linear combination of those two ended up sort of following both of them, right? Tangentially. Not a coincidence.
Is that a projection? Is y3 a projection of y1 and y2?
No. All right, so y1 and y2 are very special solutions in the phase portrait. They're both straight lines, and straight lines are not typical solutions, right? Most of the solutions with the most initial conditions follow curvy solutions. But I gave you the two straight line solutions to that system. And we're going to learn how to find those straight line solutions and exploit them to get general solutions in 3.2. Next section. All right, so what we just saw was a demonstration of the linearity principle that was discussed in the text. Here's the takeaway. For a linear system of differential equations, if you have two solutions, y1 and y2, k1 and k2 are any constants, then any linear combination of y1 and y2 is also a solution. In fact, the linear combination k1 y1 plus k2 y2 is the general solution. It's a general solution as long as y1 of 0 and y2 of 0 were linearly independent vectors. Geometrically, right, we already talked about linearly independent. The vectors are not on the same line. And algebraically, one is not a multiple of the other. And then just as a little piece of vocabulary, when y1 of 0 and y2 of 0 are linearly independent vectors, we call y1 of t and y2 of t linearly independent solutions. All right, so the linearity principle is important because it says in order to find the general solution of a system of ODEs, all you need to do is find two particular linearly independent solutions and take a linear combination of them. We have methods of finding particular solutions, right? We can use lucky guess to find at least one of them. So if you can find two particular solutions, you can get the general. And in the demo that I gave you today, I just gave you the two particular solutions, y1 and y2. In the class activities, you're going to be using lucky guess to come up with them. But don't worry, the rest of chapter 3 is going to help us develop some better analytic techniques than smart guessing. But today, that's all we have. Okay, so that's it. You can start your activities.
For